Is it working? Hey. This one's on my phone. It says I'm broadcasting. So, the what? Sure. All right. So it's 7 o'clock. We should be live. I can hear you on the phone. Should I switch to you? How do I do that? Okay. All right. Okay. All right. All right. So we will be beginning soon, or about now, actually. And so let me start with the founder, Pankaj, and he's going to share a few words. Let me switch the screen to him.
Hi, everyone. Can you hear me?
Give me a second. I'm going to actually, I think the easiest way to do this, I'm just going to move this window to the main screen. All right. Okay.
Hello.
I can hear you, but I don't think I didn't literally switch the audio to you. So I guess it will be working through my speakers.
It's okay. You can, Alex, just give an introduction of Data Cabinet initially yourself, and then keep going. Yeah.
Sure.
Okay. So I will hang up and just.
Okay. So Data Cabinet is it's a well, there are a lot of ways that you can use Data Cabinet, but in particular, well, for my purposes, it's a platform where you can where you have access to cloud CPUs and later on GPUs, so you can prepare and run your models online and do some learning from them. And also, we're trying to, and it runs for Python, R, and I believe for some other platforms. But the more important thing is that if you ever tried to, I guess, get it running yourself, there's a lot of headache and hassle But the nice thing is that with Data Cabinet, we have pre-prepared project environments where you can and you can copy their links, and they'll have TensorFlow, PyTorch, and in this case OpenAI. They'll have all the libraries and dependencies installed for you, and also there will be some example projects where you can sort of muck around with things yourselves and try to get your projects working in a very hands-on way. So it's more hands-on learning. If there's other If there's anything else important, I can check if Pankaj wants me to mention them. But otherwise, I want to continue on to the reinforcement learning part. And first of all, I guess I want to make sure that, yeah, as he said, if there are any technical difficulties in terms of logging in, then please let us know in the chat. And some people will be working to address those problems and fix it. And there were a few technical difficulties last time, but for the most part, it worked for everyone, and we were able to figure out some of the things that were some of the smaller issues that were giving people problems. But anyway, so if there are any questions, or if anyone has any issues, then just let us know. And otherwise, I'm going to continue forward onto the I guess the interesting part, the reinforcement learning part. And I'm going to structure this in a slightly different way than before. I'll try to dive a bit more directly into the OpenAI code itself, and then sort of maybe backtrack a little bit more to the concepts which you're required to know in order to understand that, and see if that's a little bit more efficient. But I guess I want to start out with just a general thing about reinforcement learning, and and the question is, when I first heard about deep learning, well, one of the biggest things that I heard other than the image classifications but one of the more interesting results was that they had AlphaGo, and AlphaGo was able to defeat one of the best Go players in the world, in spite the fact, and that's an incredible feat considering that Go's been around for thousands of years, and you can't just learn Go yourself, or at least that's been the common knowledge. You have to usually start from a very young age, and then you're building upon thousands of years of knowledge. But then they were actually able to surpass that in a way through reinforcement learning, and that sounds incredible. It sounds like, well, it's artificial intelligence learning. They're learning how to do things at least as well or better than people can themselves. But on the other hand, once you start learning, I'm sure that many of you have some familiarity by now with deep learning or machine learning or deep learning, and it seems a little bit different, because when you learn about deep learning, you learn about image classification, you learn NLP, natural language processing, and I mean but in the end, that's just a very complicated. It's just a complicated function for learning to map inputs to outputs, or probabilities of outputs, and it doesn't seem like learning at all. I mean, I guess you're learning to classify things, but when we think about learning, oftentimes it's, well, how do you learn to throw a ball, or how do you learn to walk properly? And OpenAI has examples where they have little physics simulations of humanoid beings, and they just from a reward function, they are able to figure out how to walk on their own, and that's pretty amazing. But that seems like a far cry from the deep learning, the basic deep learning that you learn about. And this is and I guess this series is a way to dive into that and understand it a little bit better, or to dive into the reinforcement learning part and to learn how you can start working with it directly. And so I'm going to go back to these slides. It's about rewards, discounted rewards, environment, agent, state, and so on. But I want to go directly into some of the code itself. So actually, maybe I should, well, and in case you're wondering, I can just log in myself just to make things simpler. You go to datacabinetsystems.ide, and then you can log in through your Google account, and I believe there's some sort of link for importing my example project, and you can go to your project manager, and then you can open your project once this sort of file button has turned green. And I've already done that, so now, and well, let me switch to, so I can look at my Jupyter Notebook directory, or my directory, and I've already opened up this OpenAI environment test. And well, the first thing is that one of the small things that we had to do at the beginning, at least, so this all works on my computer, but in order to, or on my own project, but for your imported projects, you will probably have to call this command at the beginning of your notebook. And what that is doing is it's switching the directory to the gem directory for OpenAI, and it's installing all the environments. Otherwise, it's going to have some sort of error saying that maybe it cannot find some certain gem environments which we are trying to use. And so this is some basic importing. The most important part is gem, and matplotlib, that's going to be used for the rendering, but I'll get to that. But let me first start with just the basic code, just the basic code that you use to run and render OpenAI environments. And I can switch over here. And here's a slightly larger example. And so the maybe 4 or 5 basic lines is that you have to make an environment, and that's called through gem make, and then the name. In this case, it'll be carpol, or it could be breakout. And then you can set your environment variable to that. And then the second one is that you have to initialize your environment to some sort of initial state or observation, and you can do that for environment reset. You can use that using the reset function, and that will return the initial observation. You don't have to set that to anything, but in some cases you'll want to. And then the third part is that once now that we have some initialized gem environment, we can take a look at it. So we can call at any time the render function for the environment. And this is their default method for rendering the environment. However, it doesn't quite work for Jupyter Notebook because it makes up a pop-up window. And we actually have to have some workarounds in order to make it for the notebook. Specifically, we're going to create a matplotlib box and display the input within the matplotlib. And this fourth line here, let me highlight it to you so you can see a little bit better, is that we need to choose an action. So we'll go over this, but there is an agent and an environment. The agent is whatever is choosing the behavior, and the action is whatever that behavior is. If there were no choices to be made, then it's really then there's nothing to learn. It's just going to make the only choice it has over and over again. So it's not very interesting. But in this case, we have to choose an action, and then, for example, it could be lifting your arm or moving a paddle left and right. And then we can learn, well, in that situation, for that state, was that a good action or not, or what happens when we take that action. And for the most basic case, or at least for their examples, they're just going to take a completely random action. And the way they'll be doing that is by using the action space, and then the sample function from the action space, and that will take a completely random action. If it's a discrete action space, they'll choose uniformly any one of the actions. If it's continuous, then it'll be, well, a continuous selection variable. And the last step is going to be, and the last line of code is the step function. And this is for the environment itself. You choose, once you've chosen an action, you now want the gem environment to execute that, and then you use the step action. the step function, and that will return the observation, the reward, and a done flag, which is whether it has it's reached a terminal state or not, and info, which is used for debugging. But the most important part is observation and reward. So that's the basic code, and I want to get into a few examples. So let me just sort of go through these prerequisites. And we're going to start with the popular game of Breakout, which is you have a little, it's a Atari game or where you're controlling a little paddle and you're moving it back and forth, and you're using it to, well, I'll just run it, but you're using it to hit a ball, and if the ball hits a block, then the block will disappear and you gain points. Like here, over here, I just gained a point, and well, so that was a nice example because it actually hit the ball. I believe here it's a number of lives, and you have like 5 lives or something, and I forget what this one is. And this is using, as you can see, it's using a sample action space function, so it's completely random. It's not doing anything intelligent, it's just randomly moving left and right. Not a very intelligent thing to do. So it's not going to be very successful. And so there are so the basic lines are very similar to what we mentioned. Like we have the make line, we have reset. And here we have hidden the render line, and I just want to talk about that a little bit. And as I mentioned, in order to display this in the Jupyter Notebook, then we had to create this MATLAB plot. And then, so we created this plot and IMShow, and we sent the render, the environment render output, or basically the observation, the pixels, into IMShow as a RGB array. And so you can see here that we're just displaying exact same line. We're rendering the data. We're sending it to the display, and then we're just outputting. And then we're waiting for the next output. So this allows it to continuously update it within the MATLAB plot frame. And we're doing this for, and since it's not very interesting to do this for one time step, we're doing it for 100 time steps. So that should be pretty interesting. The next example that I want to show, actually, let me mention one small thing first. It's that, so what exactly is this observation space that we're talking about here? The observation space is actually this entire image, and it is every single pixel, and it is the intensity for the red value, the green value, and the blue value for every single pixel. So it's something like a 210, well, it's right here. It's a 210 by 160 by 3 array, and it can take values from, I believe, 0 to 255. So this is actually, it's technically, you could sort of consider it as discrete because there are 255 values, and then you have to choose 210 times 160 by 3 of them. However, in practice, that's a huge space, and that's it's far too large, and it's more intelligent to treat that as more like a image, and then you apply something like a convolutional network to it. The action space is as you can see here, it's discrete 4. So there are 4 possible actions, something like moving left, right, down, and I don't know what the 4th option is. But basically, it has 4 possible options, and it's randomly sampling any one of those 4 options when it's moving. And this line isn't very interesting, but basically I just wanted to see what the reward was at any time step. You only get a reward if you hit a block in this case. So you will accumulate rewards, and you'll see whatever the value is in the top left corner. But at any given time step, the reward is only for that time step. And since most of the times the ball is just floating in the air, it's just going to be 0. So that is Breakout, and I wanted to point out a similar looking yet significantly different environment, which is the cart pull environment. And This is an example of a physics environment, and I believe it probably uses Mujoko. So these are, so first of all, this is actually a lot harder to make work in Jupyter Notebooks, but we were able to get it running, although there are certain dependencies you have to install in order to make it work. But we are using MATLAB like before, but we're also using OpenGL, and I don't recall all the dependencies that we used, but you can use, if we have a prepared set of libraries, which we basically have a pre-installed projects where you can copy them and then you can just get it running yourself. You can just get it to run yourself. And for cartpole, looks very similar to before. The only difference is that we're calling OpenGL, and so same lines in gem make. We're calling the make function. We're calling the reset function from environment, and then we're rendering it in a matplotlib window. And we're taking a random action, and then we're taking a step in the environment based off of that action. And we're just going to run this for now. All right. Let me scroll down a little. There's a small issue of clipping for some reason. But basically, you can see that you have this black cart, and then you have this wooden pole bouncing over it, and then the wooden pole falls down based off of how it's trying to balance itself. And the actions can be move left or move right. And if you move too far to the left, then of course the pole will be relatively to the right and it will fall down to the right side. And if you move too far to the right, it'll fall down on the left side. But also, if you have to account for how fast the pole is falling, because if it's swinging too fast, then you have to move it a little bit faster or more aggressively in the other direction in order to balance it again. So it's a classic sort of control problem, and one of the interesting things to note here is that this is even though we're seeing a picture here, we don't need to know every single pixel value for this. In fact, since it's a physics simulator, we actually only need to know the velocities, the positions and the velocities of the components. And in this case, components are a block, which is the cart, which is fixed on this horizontal this axis. So all we need to know is the x-axis position and the x velocity. And the other part is this pole, which is attached to it. So we only need to know the angle of the pole and the velocity of maybe the angular velocity of the pole or something equivalent to that. So if we print out the observation space, we'll actually note that this is just, instead of being a huge 210 by 160 by 3 box, it's actually just, it's a 4-dimensional array, which represents the positions, the velocities, and the angle and the angular velocities. And the action space is just discrete too, so that just means either the actions are move left or move right. And of course, the goal of cartpole is to just balance the pole as long as possible. And if I run this line here, you'll notice that it says that I reset the environment and I just ran one time step, and the reward for that one time step is 1. And this is pretty typical in the situations where your goal is to just bounce it as long as possible. And the way that you can create a reward function for that is that you just have a constant value function, such as +1, for every time step except for the terminal step. So basically, if you run it for 100 time steps, then you get a reward of 100, as long as it doesn't reach the terminal state. So that's pretty interesting. First of all, for that you can that we can represent the environment in terms of like an n-dimensional array representing the velocities and positions, and that it is rendered slightly differently and slightly more challenging to get to get it working. And so let me jump back a little bit. If there are any questions here, I don't think so. It looks like we don't have any questions, but I want to rehash some of the, I mean, we're going through these examples, and there are some important concepts which are built into these examples, and I wanted to, I guess, talk about them a little bit more, just so that everyone's more comfortable with it. And so we talked about, I mentioned the environment and the agent. And the environment is, the agent is what's choosing the action. In one of the examples for the breakout, you're moving the paddle left or right. For cart pull, you're moving the block left or right. For a game of, for a board game, you might be placing a piece down. And for a robot, you might be using some force on one of your joints or changing your joint angle. And the agent determines an action. We don't have a picture here, but the agent takes an action. If you remember in this code here, you take an action, and then, well, in this case, you tell the environment that you're taking this action, and the action is chosen. It's usually chosen based off of some policy. Given whatever state you're in, or whatever observation that you're in, you're going to say, I will choose this particular action. And then the environment takes an account that you've chosen the action, and then it will take time step, and it'll determine the new state that you're in. So that would be, in this case, would be s of t plus 1, and it'll also send back the reward, some sort of reward value for the action that you took. And I just wanted to talk about reward functions a little bit. And so when we mentioned for just general deep learning, there was, for image classification, you have some sort of loss function. You're basically trying to max or match some sort of target to your function, to whatever your deep learning model's output. And your loss function is going to be something like, how close are they? Well, then there's this question, well, what exactly, if you're learning how to walk or something like that, or if you're trying to play a game, then what exactly, what is your objective? And well, the way they define it in reinforcement learning is that you have some sort of reward at each time step, and your goal is to maximize the rewards over the total rewards over your time steps. And this is sort of based off of the idea of psychology of operant conditioning, that if you have, let's say, a rat, you could either give it some sort of reward, like some cheese, or you could give it some sort of punishment, some sort of cost, like you could shock it, or you could do something otherwise nasty to it. And that, based off of these rewards, like the larger reward, then the more favorable it will. If you reward a good behavior, then it will be more likely to do a good behavior, and if you punish a bad behavior, it'll be less likely to do that. So that is the idea behind rewards, and if you do that enough, then you can sort of get the rat to learn certain behaviors. And for reinforcement learning, we are using that concept, and our objective is, it's not just a single time step reward, it's to maximize our rewards over future time steps. So the idea is, as we learn the good behaviors better and better, then eventually we'll do it more and more, and in the long run, we will maximize our rewards by doing whatever actions gets us the most reward. And you can decide for yourself whether this is actually a realistic way of learning, or if that's how people actually learn, or and that's something you can think about. But I guess that's more of a theoretical point. And I had some examples here. For example, I mean, you could throw a ball, you could try to walk, you could move in a board game, or you could try to be picking stocks. And I mentioned picking stocks because you could sort of see that as it's sort of a nice example for future rewards, because the value of your portfolio is you can use that as your reward, and there are certainly several time steps involved, and you might do horrible at first, like you might pick poor stocks, but then maybe some sort of strategy where you pick poorly early on, but then you get to explore your different options more thoroughly. Maybe that's a more effective way of just being completely greedy and just doing whatever action you thought was best at the beginning, and then just continuing that action ad infinitum. And there's another concept which I didn't want to go over too much, but basically there's in many cases, for if there are infinitely many time steps, which you could argue doesn't actually happen in the real world or games, but if there are infinitely many time steps, you will be adding up infinitely many rewards. So then it's not very meaningful anymore. You have basically, you might have some sort of infinite value sum each time. So not very useful. So in what they tend to do for these cases, they apply some sort of geometric discount. So for each time step, you multiply the reward by some sort of discount factor between 0 and 1. And this means that you're going to converge to some sort of total future reward. And a few justifications for that is that you can argue that for future actions, maybe they're not as valuable as future rewards may not be as valuable as rewards right now. Because, and you could think of that in terms of uncertainty. You could think of that in terms of, well, if you're doing this sort of geometric summation, then it's sort of the same as having 1 over 1 minus gamma time steps. And also there's a theoretical result that if at some point for Markov decision processes, then you converge to as you keep running your Markov decision process in certain conditions, it'll converge to a stationary state, and you actually get an equivalent result with a time average result with an average reward as a discounted reward. But that's a lot of talking about that. I did want to, so that was rewards, and I wanted to just say a little bit more about environment states for this particular example. For Atari games, there's 2 ways you can think about states. One is there's the environment state, and then there's also the agent state. So for the environment state, you could think of it as the Atari game memory. So if there might be some sort of initialization, and you'll have the exact same value. If you start with that initialization, the exact same thing will happen in the game. However, you may not see that. There's also what the agent knows or sees, which is the observations, which might be the pixel values. And there might be something going on behind the scenes in terms of the game itself, which is completely deterministic. But as an agent, all you can see is the pixels that it's showing to you. And from an agent's point of view, then he's going to make decisions not based off of the absolute state of the Atari game itself, but the agent is going to make decisions based off of what they've observed. And it could be based off of the history of what they observed. Like it could be based off of in most cases for these Atari game simulations, what they will actually do is that they'll concatenate the last 4 time steps of the observations, so the last 4 snapshots of the screen, and they'll use that to represent the state. And the argument there is that, well, you don't need to know everything that happened before in a game of Breakout. You just have to know, you just need enough information so you can tell the velocities and whatnot. And that should be enough. But in general, you can concatenate all the states, actions, and rewards all together, which is called the history, and you can use that as your actual. Well, it shouldn't be state; it should be observations here. But you can use that as your actual state. Anyway, okay. So are there any questions about this? I wanted to move on to another example where we'll be doing most of the work for Q-learning. Are there any technical difficulties or any other issues? No? Okay. So I want to move on to, hopefully I won't have to log in again, but so I want to move on to the next example, which is FrozenLake. and it's a simple two-dimensional environment. And let me show the slide, which is explaining what's going on here. Well, there's a link to the FrozenLake OpenAI environment, and it is a 4x4 text grid, and they're letters representing what's in each state. The S is over here. The S is your starting point, and it's safe. And the F and H represent. The F represents frozen. So the idea is that you're on a lake, and you're trying to get to a certain point in the lake, but there are holes in the lake, and it's slippery. So if you step on a hole, then you will fall into the water to your doom, which is bad. And if you're on if you step onto the frozen surface, then you're fine because it's solid and you're not going to fall. And the question is, well, it's sort of a maze where there's certain places where you go where you just die. And so for FrozenLake, you are trying to reach your goal, and so the observation space, it's simply this 4x4 grid. So it's a discrete space of size 16, and the actions are you can move left, right, up, or down. And if you move left, so let me move back to the simulation. Okay, here we are. So here is showing the initial rendering of FrozenLake, and I've also had a little print statement which is telling you the type of the observation space and the action space. The other thing to mention is that for FrozenLake, even if you decide to go right, you don't always go right. Some probability p, you'll move randomly instead of moving in your intended direction. And hopefully this will be shown in this example that we're executing here. Okay. So here, what I did was I ran pretty much the exact same code as before, just the same simple code: observation, or reset, render, action, and then step. And we're doing it for just 5 steps. So we can see that we start in the top left corner. Our observation index is 0. So notably, the observations, you can infer this from what's going on, but the way the indexes work is it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. So you can see in this orange square below, the observation index is 4, like I mentioned. And if you go down another row, it's going to be 8. And if you move right, it's going to add 1. So it's going to be, so this row, this square right next to the right of the starting point, the observation index will be 1. And anyway, so for the first step, the action, it says that it decided to take the action left. And the action left is, well, first of all, you can't go left because you'll clip out of bounds. So if you actually take the action left, you'll just return to the exact same state, so you won't move at all. And if you also, similarly, if you moved up, you'll not move at all. But you can see here that it decided to go left, and it's frozen, so the slippery component came into play, and it randomly moved down instead of left. And so it ended up in the square below. And then over here, it also tried to go left again, so it should have ended up in the same square, but it went down again. So it went down again because of this non-deterministic nature. And also you can tell that action index 0 is supposed to be left. So 0 is left, 1 is, I think 1 is down, and 2 is right, and 3 is up. So let me move down a little bit more. Oh, okay. So at the next time step, it decided to move, it tried to move left, left, right. So it tried to move right, and instead of moving right, it was slippery, so it moved down instead, and it fell into a hole. And you can see over here, once it tried to move from the hole, then it tried to move down and it tried to move up, but to no avail. Once you're in the hole, you will stay in that state. Let me try it again, and we're going to reiterate it again. So just to see if it will move a little bit more deterministically this time. And here it moved down, and then it successfully, then it tried to move right, but it actually went up instead. And then it tried to move right and it went down again. And then it tried to move down and went right instead. So overall, you can see that it is oftentimes it is not moving in the direction that you sort of expect. So that's an example of what's happening in FrozenLake, and just to prove to ourselves that it's moving stochastically, I'm going to actually choose the actions. Now that we've known that the actions are 0, 1, 2, and 3, and what they represent, left, right, up, and down, or left, down, right, and up, we're actually going to decide to choose the actions. So first we're going to move left, then we're going to move down, then we're going to move up, and then we're going to move to the right. And we'll see what happens here. So here, we tried to move left and we went down instead. We tried to move down and we went right instead. And then we got stuck in a hole. So let's try it again. We tried to move left, then we tried to move down, and it went, instead of moving down, it just stayed in place. That's because it tried to move left. And then it tried to move up and it went right instead. And then it got stuck there. So you can see it's, as what I was trying to point out, that it's not it doesn't move in the way that we expect. And that's the frozen part of the frozen lake. And it's interesting, but it's actually kind of frustrating for one specific reason. It's that for the OpenAI environments, there's no way, even though we know what for this specific environment, we know exactly what the observations are. So we pretty much know what the states are. We can't directly set the state. There's no function that I know of that will allow you to do that. So, and this is an issue because once we start doing value functions, we actually want to determine what the value of each state is. And I'll explain that a little bit later. So let's say I do actually want to get to any particular state. So what I'm going to do is I'm going to create a sort of a spin-off of the FrozenLake environment, but there are a few options if you look at the code for the FrozenLake Python file, and one of the tags is called isSlippery. And what we're going to do here is we're going to set isSlippery to false. So now it will no longer be slippery, so it will be completely deterministic. And we're going to run this. Okay. And now we're going to test it out again and see if it will actually move the way we expected. And we're going to move, let's see, 2 is right, and then 1 is, we're going to try to move right, and then down, and then left, and then down, and then right, and then up. So we're going to do this. Run this here. And as we'll note, it moved as we thought, right, down. Scrolling can be a little difficult, but it moved right, down, left, down, right, and up, which is pretty much what we said. And now we can see that, yes, it did indeed move right, and yes, it did indeed move down, and got stuck in this hole. And from that, it couldn't move anymore. We tried to move left, we're still stuck on the hole. Move down, still stuck on the hole. Tried to move right, we're still stuck on the hole. So it did exactly what we wanted to. So it's sort of it's a way of playing around with it that will indicate that it's actually behaving exactly the way you expected it to. And so now this is sort of nice in the now that it's deterministic, we can actually, even though we cannot directly set the observation state, in the deterministic case, we can now sort of predefine some trajectories to tell, in order to, since it always initializes in the top left corner, we can tell it to move to any particular position that we want. So we can, and we're going to do this by defining paths for each particular tile. For example, if we want to move to this square over here, we just move right once. And if we want to move to the 2 squares over, we just move right twice, and it's going to be some combination of moving right and down and so on. So I created a nice little function to do that. And for example, if I want to move to this 3rd square on the bottom, that is 3, 7, 11. So now I can test whether it moves there, and yes, indeed it moved there. And if I want to move to 12, which is the bottom left square, let's see if that works. Yes, indeed, it moved to the bottom left square. And if I want to move to the goal, the bottom right square, okay, and it moved exactly where I expected. So yeah, this is a very, so now we actually have some control. We can now move around the environment in a way the way that we want. And now this brings us on to the idea of value functions. So for value functions, basically the idea is that if we, given a certain policy, if we move to any, once we move to any particular state, we know that we can, if we run the policy from that particular state, so let's say we're in this state, this state F, which is to the top, which is left, 1 square left and 1 square above the goal, then if we run our policy from there, then the question is, well, on average, what is the future reward if we use our policy to decide action, a pre-specified policy to decide actions? And the way we can do this is that all we have to do is we can set ourselves, the simple way to do this is that we can start at that particular state, and then we can just run what we call a Monte Carlo rollout, or we can just run a rollout where we, for a certain number of, for hopefully enough steps, we're just going to take the action defined by the state. We're going to use our policy, feed into our policy function the state, and then the action probabilities, which is going to be a large, well, I guess it'll be a large array, which says that at any particular state, what's the probability that you'll take this particular action? So we can run that action. We can sample from that. We can choose a particular action, and then we can take a step based off of that action, and then we can add our the reward to what we'll call our value function, and we'll do that until we finish. And so that's one particular run from that state, and it might get some reward of some total reward, and then we'll do that a whole bunch of times and average it out, and that will give us the average total reward from that state, and that's what we will call our value function, and or more specifically our state value function. And we can do the exact same thing, but but instead of just choosing a state, we can choose a specific state and choose a particular action. And then given a predefined action at that specific state, then we can do the exact same thing, and we can do this rollout and determine, and then we can have some sort of we can average out the future rewards for that state action pair. And if we know this, so the whole idea behind this is that if you have, once you have this value function, you don't need to run, you have this idea of how, if you move to any particular state, how valuable is it, or what do we expect in terms of how much additional reward we can gain by once we've moved to that state. So we don't have to run the entire policy for the rest of this. We don't have to roll out the policy and do all those time steps once we have the value function. We have some sort of average value of what's going to happen there. And in particular, for the state action version, once we know for any specific state, if we know the value of every particular action, then let's say there's a very simple way of determining of creating a better policy, and that is if we know all the value functions, if we know all the action values, we're just going to choose the best possible action value for each state, and we call that our greedy algorithm, and we can use that as a new policy. So that will be and that will be well, that's a very simple way of what we call policy improvement. So this step here where we're running this so given a policy, we're determining the value function, we call that policy evaluation. And you don't have to use Monte Carlo. There are other methods of doing it. A very common one is based off of Bellman's equation. That's called temporal difference learning. And for that, instead of doing this, instead of rolling out for a large number of steps, what you would do instead is that you would take the reward, and then you would add the discounted value, the expected discounted value function for the next state that you expect to find yourself in. I should give a formula for that, but I can put that in the PowerPoint slides later. So that's the value function. Well, so that's an example of policy evaluation, and you could see here that I created some code for the FrozenLake policy evaluation, and I just need to implement some sort of policy where I define some sort of action probabilities. I define the probability for each action, and then it can sample from that and then choose the actions, and I can run this Monte Carlo rollout for the action values. So that's a policy evaluation step. And the second part is the policy improvement step. And I mentioned, I guess I mentioned during this that one method to do that is this greedy algorithm, where you just choose amongst all possible actions for a given state. You just choose the best action, and that is one example of policy improvement. And there are other ways of doing that as well. You can use a policy gradient as well, and there are a lot of different ways of doing that. And in general, reinforcement learning is based off the concept of policy iteration. And there are two steps to policy iteration. One is policy evaluation. You evaluate the value functions. And the second step is policy improvement, where you improve your policies. And I guess that is, let's see if there are any questions. I guess not. And so that is, so what I described there, this Monte Carlo evaluation, and then some sort of policy evaluation, and then some sort of a greedy policy improvement. That is the basis of Q learning. For Q learning specifically, instead of estimating the value function, the state value function, you have some sort of representation. You have basically a table for your state action value functions, and then you do you evaluate them either through Monte Carlo or through temporal difference learning, and then you do a policy, and then you do a epsilon greedy policy update, which is you greedily pick the best action with almost all the time, but with a small probability of the time epsilon, you will pick a completely random action instead. And that's called epsilon greedy and the idea behind that is that it gives you, it allows you to explore, it allows it gives you enough exploration that you know that for for linear cases, for tabular cases, that you will converge to the optimal policy. And then it's basically what they're using for Min's DQN paper for Atari games, I think from 2015. And I wanted to wrap it up by mentioning the last few things. There are a few details in order to make this work. As you saw here, we had this inconvenient issue where we had to, where technically, if we really want to evaluate every possible state for the value function, then we're going to have to, we're doing this very dumb method of going to each state and then doing a rollout from there. But what you'll do in practice is some variant of experience replay, where you're going to you're going to keep a record. You're going to do these rollouts, but you're going to you're going to come up with trajectories for each rollout. So you'll run your simulation starting from your initial state, and then you'll record each of the state's actions and rewards. And so you'll have some sort of history of that. But now you're going to use that history to update. You're going to parse through that history, and you're going to, for the Monte Carlo version, you're going to use that information to update your, at each time step, you're in a particular state, and you're going to update the value function for that state. And for the temporal difference case, what you're going to do instead is that you have the exact same trajectories, but you're going to split the history up into, I think, quadruplets of state, action, rewards, and then the next state after that. And then you're going to run temporal difference for your policy evaluation instead of Monte Carlo. So instead of rolling it out for all possible time steps, you're just going to update it for one specific time step at a time, and you're going to sample from. So you do your rollouts, and then you break them up into little pieces, and then you add them into something called your replay buffer, and then you sample from your replay buffer, and you by sampling from the replay, you do temporal difference updates from the replay buffer, and that's one of the main keys for I guess for most Q-learning algorithms. And the second piece is for if you want to, let's say, make the Atari games work, is that this works very nicely for something like FrozenLake, where you have a discrete number of actions. You have discrete actions and a relatively small number of discrete states and actions. But for the Atari game case, you have pixels for your states / observations, and that's way too large. So instead, what they do instead is that they have to, if you want to run a policy gradient, you do some sort of parameterization. But for DQN, they have to decide to sample some of the states more than other states, and that gets into this idea of, well, first of all, they have to run a CNN on the pixels or on the pictures on the images in order to create a simpler output, in order to create like a simpler observation. And the other thing is that so they have to run a CNN, and they have to do one other thing. What was it? Well, I can't recall it this time. It's something like it's mostly they have to run. They have to use a replay buffer, experience replay buffer, and they have to use a CNN. Oh yeah, and they have to use something called. They have to think about their sampling. For their experience replay, they are preparing trajectories, but they may be from some older policy, which is a small difference. So technically, the trajectories that they're sampling from are from different policies from what they're using before, so they're off policy. So they're basically weighting certain states more than other states based off of their off policy trajectories. But anyway, that's sort of I guess the last part's just sort of a short discussion type wrap up of what you would need in order to make DQN work. We actually have most of the tools here in order to make for the simpler tabular cases like FrozenLake in order to you can easily, once you have this value function, or you can create a very similar action or a Q function, which is a state action value function, and then we can just take we can just do this policy iteration update based off of the state action value function, and that's mostly what I wanted to cover. The idea behind this was more to just expose people early on to just get people comfortable mucking around with OpenAI Gym, and then playing around with it, and then giving them a basic example of how to estimate or how to do a rollout of a value function or an action value function, and from there, then you can you can sort of come up with your own methods of improving your policy, of evaluating your policies, and then improving your policies, and that's the very basics of reinforcement learning. And I guess that's what I have for today. I wanted to do something more direct and with less discussion, something a bit more hands-on than before. And we can see if there are any other questions, and I can move it back to Pankaj. Let me. So is it still working? Okay. We can actually, while I'm waiting to see if there's any comments, we can bring up some more interesting environments. Like we can probably get Flappy Bird to work. Oh, this may not be one of their core environments. Maybe it is. Here's a example of Space Invaders, and we can do something similar we can run a very terrible random policy for Flappy Bird. Let's see. Okay, this one is probably a third-party one, so it's I don't think it's included with the rest of their environments. But anyway, there is nothing else. Then I guess just please leave comments or just contact us, and we can answer any questions or we're happy to listen to any suggestions. And I guess this Sunday we'll try to do we'll try to move on to, we'll give some more examples of Q-learning and also move on to policy gradients, which is sort of the other broad major method for reinforcement learning. And I mean, once you have both of those, then you can arguably you have the two general methods or two of the main general methods for creating reinforcement learning algorithms, and you can play around with that, and after that we can discuss some more complicated algorithms which deal with some of the issues of stability or sample efficiency, which is actually a bit more problematic for many of these reinforcement learning algorithms. But anyway, just leave any feedback, and other than that, just have a good night. Thank you.